In this video, we'll be looking at executing the simplex algorithm. I'm going to do it in this video on a two-dimensional case so that I can refer to the graph as we go. Here is the simplex algorithm. So first of all, we're going to choose a pivot column. Explain all this as we go. Then we're going to conduct a ratio test. Then we're going to choose the smallest ratio test value. That will give us a pivot. Then we're going to pivot around that chosen point. And then if there are no negative values in your objective row, we have completed the algorithm. Otherwise, we've got to repeat all of those steps again. This is the step where you are most likely to make an error. That's pivoting, because it is so easy to make a sign error, as you will see in the upcoming steps. So just be really vigilant with carrying out this algorithm. Okay, so just be really careful not to make a silly arithmetic mistake. Okay, all right, so here is the linear program that we are going to solve. Now, I've already solved it graphically. This was done in a video back in the graphical linear programming solutions section of modeling with algorithms. And I'm going to be referring to this as we go through this algorithm. Okay, so in the previous video, what I did was I took this this linear program and I created the initial tableau. Okay, so if you've not checked that out or you're not sure where this tableau has come from, then do please check out the previous video and you'll see where this has come from and why it is what it is. In this video, we're going to look at moving from tableau to tableau. Now, I talked in the last video about basic variables and non-basic variables, but I didn't define them, and that's because I can't do that really until I get to actually doing the algorithm. So what we've got is at the start of the simplex algorithm, x and y are referred to as non-basic. And everything else is basic. Okay, so S1 to 3, the three slack variables are basic, and P is basic. In fact, P is always a basic variable. Now, what that means, what this table represents is it represents 4 equations in 6 unknowns. 1, 2, 3, 4, 5, 6. 6 unknowns, 4 equations, which means that mathematically we have 2 degrees of freedom. We can choose 2 of these variables to be any value, and that will then lock in the other 4 values. So what we do is we choose values for the non-basic, because the non-basic columns are the columns that are full of junk. If we omit those 2, then what we are left with is a 4x4 in this case, matrix, if you like, of 1s and 0s. And what we can do is we can read off the 1 and we can read off the value on the right hand side. So if we're going to set x and y to be 0, which we are going to choose to do, because you always choose the non-basic variables to be 0, then what we are left with is p equals 0, s1 equals 21, s2 equals 75, and s3 equals 82. That's where we are at. So if x equals y equals 0, so that's our choice, because we are free to do that, because we have 2 degrees of freedom, then that locks in the others as being p equals 0, s1 equals 21, s2 equals 75, and s3 equals 82. Okay. Because x and y equals 0, we are here at the origin. And this is why the origin needs to be part of the feasible region, as mentioned in the previous video for simplex, because we start at the origin. Okay? If you're starting at a point which is not in the feasible region, then that's an issue, and you need to do something different, which we will look at later on in the course. Okay? But for now, we have to have the origin as part of the feasible region. All right. So now that we've got that out of the way, we are going to conduct the simplex algorithm. So the first instruction for the simplex algorithm was to choose the pivot column. Now the pivot column is going to be the column that has the most negative value in the objective row. Okay, so look at the objective row, which is this row here. It's the first row with numbers in it. and the one with the most negative value is this one. So therefore, this is the one that we are choosing to be our pivot column. Okay, put an arrow above it and actually do that just to show that you are selecting that column. Okay, so that's the first instruction. The second instruction is to conduct a ratio test. Now the ratio test is the right-hand side value divided by the pivot column value. We denote it by the Greek letter rho. So to the right-hand side of the table, pop in a new column header called rho, and we are going to conduct the ratio test. So 21 divided by 1 is 21. 75 divided by 5 is 15. And then 82 divided by 8 is 41 quarters. Okay, or 10.25. From the ratio test, you choose the smallest non-negative value. So let's go back to my instructions a second. Point 3, we're going to choose the smallest ratio test value that's greater than or equal to 0. And I put a little asterisk here and at the bottom of the page. Sometimes we choose 0, sometimes we don't. I'll address this in a future video. Okay, so for now, we're not actually going to meet any zeros in the ratio tests for this problem, but I'll address when we do in a future video. Okay, so we're going to choose the smallest non-negative value. So that's 41 fourths, because that is 10.25. So that's the one that I am choosing. And that then chooses the pivot row. So I've got a pivot column and I've got a pivot row. The element that is in both the pivot column and the pivot row is defined as the pivot. So there's my pivot. Okay, P-I-V-O-T, pivot. The next instruction is to pivot. Okay, so I need to explain exactly what that means to get from one tableau to the next. Okay, so before I move on, just want to explain what this ratio test is doing. It's testing how far I can move in the y direction, because the y direction is the direction I'm choosing, before I hit a boundary. So I can move y21 before I hit this boundary, or I can move y15 before I hit this boundary, or I can move y as 10.25 before I hit this boundary. Looking at the graph over here, I'm moving in the y direction, because that's the column I've chosen. I can either move 10.25, which will take me to this point. I can move 15, which will take me to the intersect of this line with the y-axis, or I can move 21, which will take me to the intersect of this line with the y-axis all the way up here. The problem is I don't want to leave the feasible region. So I've got to take the smallest one, because if I take any others, I would have shot out of the feasible region, and that's not good. Okay, I can't leave the feasible region. I've got to remain in the feasible region. So this is why we take the smallest value from the ratio test, okay? Because I don't want to leave the feasible region. Okay. All right, now to conduct an iteration of the simplex algorithm, what I'm first going to do is I'm going to define the pivot row as PI. And now the pivot row is going to be the row that the pivot is in from the previous tableau, divided by the value of the pivot, so that this is the number 1. I want the pivot value to be the number 1. And what I'm going to do is essentially I'm going to try and make this column, which is currently -2158, look like this column, 0001. Okay, so I'm going to transition 0001 to this column here. Okay, so divide it all by 8. That will make this a number 1. That will make this then an 8th. 0 divided by 8 is still 0. That's a 0. That's a 0. That's an 8th. And that will actually be the value of the ratio test from before. So it's 41 quarters. And I've defined that as PI, the pivot row. Now, my desire is to make the pivot column zeros everywhere except for my pivot value. That's what I want to happen. Now, because each of these rows in the tableau represents an equation, I can just add and subtract multiples of an equation or a row to another. So what I'm going to do is I'm going to take row 1 of the previous tableau, Okay, I'm going to shorthand it to row 1, and I'm going to add 2 times the pivot row. So what that's going to do is it's going to do -2 plus 2 times 1, which will be 0. So I'm forcing this number out to be 0 by adding 2 multiples of this to this. Do the same thing to this one, except I don't want to add 2 multiples of the pivot row. I want to subtract 1 multiple of the pivot row. So I'm going to denote that as row 2 subtract the pivot row. Okay, that will be the 1 minus the 1, which will make that a 0. And then finally this one, I've got a 5 here. I want to make it a 0, so I'm going to subtract 5 times the pivot row. So row 3 minus 5 times the pivot row. And PI here, the pivot row, is defined as this row here. Okay, that's just the original row divided by 8. Okay. All right, now I just carry out these 3 instructions to the whole row. But I can shorthand a little bit because there are some shortcuts that I can make. Anything that was a 1 and 3 zeros before will remain as a 1 and 3 zeros, except for this one, which is going to change. Because what I'm doing is I'll be adding multiples of 0 to those rows, or those elements. Okay, so they're not going to change. They're going to remain 1, 0, 0, 0, 1, 0, and 0, 0, 1. So I can just fill those out. 1, 0, 0, 0, 1, 0, and 0, 0, 1. So now I've only got 1, 2, 3, 4, 5, 6, 7, 8, 9 elements to find. Okay. All right, so let's find those elements. And I'm going to do that by following this instruction. Okay, so I've written it to the left-hand side of the tableau. You can do that, of course, in the exam. That will help you to remember exactly what the process is that you are trying to do. So row 1, so that was the number -1, plus 2 times the pivot row. And the pivot row is in red down here, is an 1/8. Okay, so row 1, which was my old value, plus 2 times my pivot row. So that gives me -3/4. So the number that goes here is -3/4. And I'll just repeat that process for all of the other elements in that row. So S3, that was a 0. And now I'm going to plus 2 times the pivot row, which is an 1/8. So that's just a 1/4. Hopefully you can appreciate why it is so easy to make a mistake now. And then finally, the right-hand side, apply that same rule. We're going to have 0 plus 2 times 41/4. And that gives us 41/2. Okay, so that's the first row. And now we'll just repeat the instructions for the other 2 rows. So this time it's row 2, subtract the pivot. So row 2 was the number 1, and we're going to subtract the pivot, which was an 1/8. So that's 7/8. That goes in there. 0, subtract 1 times an 1/8 is obviously -1/8. All right. Some of these you might not need a calculator for. And then finally, we've got 21 subtract 41/4. And that gives me 43/4. And then finally this row here. So we're going to do the old row 3, subtract 5 times the pivot. So the old row was 3, subtract 5 times the pivot, but the pivot is an 1/8. So that's 19/8. And then we do the same thing here. So we're going to get 0, subtract 5 times the pivot, which is an 1/8. That's -5/8. And then finally, we're going to get 75 minus 5 times 41/4, which is 95/4. And there we go. That is an iteration of the simplex algorithm. So basic variables and non-basic variables have now moved. Okay, so this is now non-basic, still non-basic, I should say. These 3 are now basic. This one is non-basic, and P is always basic. Okay, so we can see what's happened is S3 was basic, is now non-basic, and Y was non-basic and is now basic. That's because we've moved in the Y direction. So where are we on the graph? Well, just as before, we chose the non-basic values to be 0. We're now going to choose the non-basic values to be 0. So these two are the ones that we choose to be 0. So x equals 0 because that's non-basic. It's a column full of junk. And S3 is non-basic because that's a column full of junk. If we then omit those two columns, then we're left with, again, a grid of 4 ones and 12 zeros. And each one occurs once in each column and each row, which is standard. So then we can just read them off. So P is equal to 41 halves. S1 is equal to 43 quarters. S2 is equal to 95 quarters. And Y is equal to 41 quarters. So where are we on the graph? Well, we've moved from x equals 0, y equals 0, which is the origin, to x equals 0, y equals 41 quarters. So we've moved from here up to here. Okay, so we are now at this point, at the point A. Okay, that's what's happened graphically. At the point A, P has the value 41 halves, and you can take x equals 0 and y equals 10.25 and put it into here, and we get indeed that what P is 41 halves, or 20.5. What else have we got? S3 is 0. That's because we are now on this boundary, so there's no slack left because x plus y equals 82. So we're not, there's no slack left. We're on the boundary. But S1 and S2, there is still slack, and that's because we are still a distance away from those two inequalities. Okay. So that's what those represent. Okay. If a slack variable is positive, then we are not on the boundary. If a slack variable is 0, we are on that boundary. Okay, and the final step of the simplex, if there are no negatives in your objective row, you are at the optimal vertex. Otherwise, repeat the algorithm. Okay, so objective row, that's this row here. We do have a negative, so we are not at the optimal vertex. So therefore, we must repeat the process again. So let's repeat the process again. I will do it a little bit quicker this time. So that is the only negative value in the objective row. So therefore, that must be my my pivot column. Once I've chosen my pivot column, I need to conduct a ratio test, which is the right-hand side divided by the pivot column entrance. What I didn't mention earlier was you don't conduct a ratio test on the objective. You never pivot on the objective row. It's always the constraints. So we can ignore the top one. So the ratio test values then, we're going to have 43 quarters divided by 7/8. That is about 12.3. We're going to have 95 quarters, and we're going to divide that by 19/8, and that is 10. And then we're going to have 41 quarters, and we're going to divide that by 1/8, which is 82. And from the ratio test, we choose the smallest, so we're going to choose this one here. Okay, so that's our pivot column. This is our pivot row. Therefore, this is our pivot. Now, to make that a pivot, we need to take that whole row and times it by 8/19, because in doing so, that will make that entrant number 1, which is what we want. Okay. So 0 times 8/19 is obviously 0. That's going to remain as a 0. That's going to remain as a 0. That's now 8/19, and that is going to be minus 5/19. And then I also need to do 95 quarters times 8/19, which is 10. Okay. So that is now my pivot row. I'm going to call that PI. Obviously, I've got the luxury of colours. You don't have that in the exam. Again, quick shortcut. Anything that was a pivot column before remains as a pivot column, except for S2 this time, because that 1 is going to move over here. But Y is going to remain as 0, 0, 0, 1. S1 is going to remain as 0, 1, 0, 0. And P is going to remain as 1, 0, 0, 0. Okay. So we've got these 9 elements over here to fill out. We know that this is going to be 0, 0, 0 as well, because that's what we're going to force out. Okay, so just as before, to write the instructions out, ignore those now. PI is defined as this row. So to get rid of that 3/4, I need to do row 1 plus 3/4 times the pivot row. To get rid of the 7/8, I need to do row 2 subtract 7/8 times the pivot row. And then to get rid of the 1/8, I need to do row 4 subtract 1/8 times the pivot row. So those are the instructions I'm carrying out this time. Okay, so calculator. Row 1 plus 3/4 times the pivot. So I've got 0 plus 3/4 times the pivot. Now the pivot is 8/19. So that value is 6/19. Oops, let's do this in blue. So we get 6/19 in there. The next one, we're going to have 1/4 plus 3/4 times the pivot, which is minus 5/19. Just be really careful with any sign errors. It is so easy to make one. The right-hand side was the number 41/2. And then we're going to add 3/4 times the pivot row, which is 10. So that is 28. That's the first row gone. Second row, 0 minus 7/8 times the pivot row. The pivot row is 8/19. So that's minus 7/19. Then we've got negative 1/8 minus 7/8 times the pivot row, which is minus 5/19, which is 2/19. Oh, notice I said earlier that the variables can never be 0. The elements can be in here, but the right-hand side will never be 0. Okay, the actual values of x, y, the slacks and the p will never be negative. But the entrance can be negative, so just bear that in mind. 43/4 minus 7/8 times the pivot, which is minus 5/19 is, ooh, that doesn't look right. Try that again. 43/4 subtract 7/8 times, 10. Happens if I get the right column. 2. And then this one here, I've got 0 subtract 1/8 times the pivot, which is 8/19, which is minus 1/19. Then I've got 1/8 subtract 1/8 times the pivot, which is minus 5/19, which is 3/19. And then this element here is 41/4 subtract 1/8 times the pivot, which is 10. Okay, so that finishes the second iteration, or the second tableau. Just the 0th tableau, first tableau, second tableau, or 0th iteration, initial tableau if you like, first iteration, second iteration. Okay, right, so what have we got this time? These 3 are basic. Oh, sorry, actually, those 4 are basic. And these 2 are non-basic. So we're going to set S2 to equal S3 to equal 0. That's our choice. We have our 2 degrees of freedom. We choose those 2 to equal 0. And that leaves us with P is equal to 28, S1 is equal to 2, X is equal to 10, and Y is equal to 9. Okay, so where are we now in our graph? Well, we're at 10, 9. Okay, so we've moved from the point here, the point A, to the point 10, 9. So we've moved along this constraint, and we are now here at the point 10, 9. Now, at the point 10, 9, P is 28. If we plug X is 10 and Y is 9 into here, indeed we do get P is 28, so that's always a good sign. We've also got S2 and S3 are both 0, and that is because we are lying on both of those constraints. So S3 was the constraint from, the slack from this constraint, and S2 was the slack from this constraint. And because we are on that boundary, or on those boundaries, the slack from both of those will be 0. S1 is 2, that's because we are not on this boundary, so there is some slack left here in the top one. S1 is 2. And if you plug in x is 10 and y is 9, then that comes to 19. So we can see we're 2 away from the 21. So that's what that represents. And that's everything. Okay. Are we at the optimal vertex? Well, let's just go back to the instructions one more time. If there are no negatives in your objective row, you're at the optimal vertex. Objective row, there we go, there's no negatives in there, so therefore we are at our objective vertex. So no negatives in the objective column, or sorry, objective row. Therefore, we are at the optimal solution, or optimal vertex of the simplex. Okay. So the solution then to the linear program, we don't actually care about what the slack variables are. We just care about what p is. So p is equal to 28, and this occurs when x equals 10 and y equals 9. Okay, so we have solved this linear program now using the simplex algorithm. And yes, I've drawn the graph for reference, but you wouldn't need that in the actual execution of simplex. Okay. So there, that's the simplex algorithm. I hope you appreciate how easy it is to make an error. It is so easy to do. Just be really careful, really vigilant, and I do recommend writing the instructions down for what you're doing on the left-hand side, because it just really helps you to refer to that each time you're doing a calculation. All right. Also, don't forget your shortcuts of filling out the ones and zeros in each iteration, because that will save you a good amount of work. Okay. If you have any questions, please pop them in the comments below. There will be more videos to come on the simplex algorithm, so please check those out if you haven't already. Thank you very much for watching.